Hi, everyone, and welcome back. We're going to be talking today about hypothesis testing, or null hypothesis significance testing, as it's also called in our reading. So what is this thing? What is hypothesis testing? Well, at the heart of the scientific process, there's this constant reassessment, constant challenge, where the idea of science is to constantly experiment and re-experiment and examine our assumptions, examine our understanding of the world around us, and when we find that understanding insufficient, to try to find better explanations that do a better job of explaining the world that we observe. This is a little bit challenging because there is uncertainty built into everything, right? We can't be certain of how things will work out, even if we have a very good understanding of all of the underlying processes. So, in this drive to reject outmoded or insufficient explanations and replace them with better, improved theories, we have to have a method of going forward. And hypothesis testing is the idea that gives this whole scientific process a solid statistical grounding. But it's subtle, so we have to be a bit careful in thinking about it. What I'd like to talk about today is just what null hypothesis means, what we use, what the hypothesis testing is, and how we kind of quantify the things that we see in experimental results. So we start with what we call the null hypothesis. The null hypothesis represents our baseline understanding of the world around us, or any of the current understanding, whatever the kind of basic, no special explanation is needed version of reality is. So the null hypothesis is the thing that we start with, and it's often abbreviated by H0, H with a zero subscript. So H for hypothesis, and the subscript 0 is null, or naught, or nothing. To show that what our goal is in scientific experimentation is to show that the null hypothesis is incorrect in some way. The way we do this is by running experiments and then obtaining results that are very unlikely if the null hypothesis is true. Of course, this is hard to do if you don't have a better explanation than the null hypothesis. But if you have an alternate explanation and you think it's true, then it shouldn't be too hard to engineer a situation in which you're very likely to get results that are well explained by your explanation, but very poorly explained by the null hypothesis. You try to find those differences between the null hypothesis and your alternative hypothesis. And so that's the experimental setup that we try to do. So let's think of an example. We're going to go back to our old standby, flipping a coin. So let's say that I pick up a coin and I'm considering flipping it. The null hypothesis for this coin is that it's unbiased. You don't just assume, walking around the world, that all of the coins are biased in some way. Instead, you assume, yeah, they're all pretty fair. And you need to see evidence to convince you that that's not the case. So the null hypothesis is exactly that kind of thing. The kind of thing that you would need to be convinced to reject, that you would just assume is true if all else was left the same. So our assumption for this coin is that it is unbiased, meaning that it is no more or less likely to land heads than tails. That's our H0. That's our null hypothesis. But if I suspect that that's not the case, I want to set up an experiment that will let me show it, that will let this coin show its true biased colors. So if I can think of such an experiment, then what am I going to do? I'm going to run the experiment, and if the results that I see are very unlikely under the null hypothesis, so if the results that I see are very unlikely to happen if the coin is actually unbiased, then I will be allowed to reject the assumption that it's unbiased. I'll be able to reject the null hypothesis. If, however, the results are not so unexpected, then I retain H0. I retain the null hypothesis. The way we say this usually is we fail to reject the null hypothesis. So let's think of a specific experiment that I could run on this coin, and that's going to be to flip it. I'm going to flip the coin a bunch of times, 10 times. So it's not that many times in reality, but let's say that I flip this coin 10 times, and I want to know if I look at the results. So I could have anywhere from 0 to 10 heads in this coin flipping experiment. And suppose that I got each of these results, would we reject the null hypothesis or not? So for example, if I happen to get 5 heads in my 10 times flipping the coin, would it be safe to reject the null hypothesis that the coin is unbiased? Right, so let me just to make a notation here. So H0 is that the coin is unbiased. So would I reject that hypothesis if I got 5 heads? Is 5 heads very unlikely if the coin is unbiased? And of course it's not. It's the expected value. It's the thing that's most likely to happen. It's not going to happen every time, but it is the most likely outcome. So if we got 5 heads, no, we would not reject the null hypothesis. We would fail to reject H0. Fail to reject the null hypothesis. So we would just say, yeah, haven't seen any evidence that it's not a biased, that it's a biased coin. So I'm going to stick with the assumption that it's unbiased. If, on the other hand, I got 10 heads in my experiment, then I would say, yes, that seems to me like a biased coin. If I flip a coin 10 times and it comes up heads every single time, that's an unlikely thing to happen if the coin is actually a 50-50 chance to get a head or a tail each time. So yes, if I got 10 heads, I feel very confident saying that I would reject H0. I have a biased coin on my hand, probably. What if instead I got 1 head? Well, that's still pretty unexpected if I have a fair coin, 1 head and 9 tails. So I think in that case, I would also reject. All right. What if instead I had 6 heads? Now that's pretty close to the expected value. How surprised would you be if you flipped a coin 10 times and it came up heads 6 times? Not very surprised. So without doing any calculations, I feel pretty confident in saying this is well within the range of expected things that could happen if you flipped a fair coin 10 times. So in that case, no, I'm not going to reject. So no, fail to reject. Now, what if I got 7 heads or 8 heads? Somewhere in here there's a line. Somewhere there's a line between, well, this is kind of unlikely to happen with a fair coin, and this is really unlikely to happen with a fair coin. So these cases down here, these are a little murkier. They depend on how much evidence you need to decide that you're changing your mind about something. 7, 8, 9. In these situations, would you be happy to reject the null hypothesis or not? And this murky situation is why we need a little bit of probability and statistics. This is why we've been looking at combinations and permutations. It's going to allow us to calculate some relevant probabilities for this exact kind of situation. So we need something a little bit more concrete if we're going to go forward from here. That thing is called the p-value. The p-value of an experiment is how likely is the given outcome or something more extreme to happen, assuming that the null hypothesis is true. So if I had a fair coin, how likely would it be that I got 7 heads or something more extreme than that? So let's change the situation a little bit. Let's just say, okay, for our coin, what the p-value of getting 9 heads would be however likely it is that a fair coin would produce a result as extreme as 9 heads. So what do I mean by as extreme as 9 heads, or as extreme or more extreme than 9 heads? Which outcomes would qualify as being as extreme as 9 heads or more extreme? Well, obviously 9 heads would qualify. And more extreme than that would be 10 heads. But it's equally extreme to get 9 tails if you have an unbiased coin. Because heads and tails are equally likely. So 9 tails is just as extreme as 9 heads. It's just as far from the expected value of 5. And similarly, 10 tails is also just as extreme. So 9 tails is equal to 1 head, and 10 tails is equal to 0 heads. Okay, so that's the collection of things, the collection of events that qualify as extreme or more extreme than 9 heads. So the p-value for 9 heads would be how likely is it that one of these things would happen if I flipped my coin 10 times. Now I can do a little calculation on this. I'm not expecting you to be able to do this calculation on your own just now, but we will soon be able to do this. Basically figuring out these probabilities. I'm going to write down what the calculation is, and maybe you can come back to this after we've covered the probability calculations a little bit more often. So the 9 heads would be 10 choose 9 times 1/2 to the 10th power. Right, so there's our combination, our choose coefficients that we've been talking about. The 10 heads would be 10 choose 10 times 1/2 to the 10th power. 9 tails would be 10 choose 1 times 1/2 to the 10th power. And then 10 tails would be 10 choose 0 times 1/2 to the 10th power. So I've multiplied this out, and it turns out it comes out to 22 over 1024, which is approximately equal to 0.0215 or 2.15%. Does that seem low enough? Is that a rare enough event to reject the null hypothesis? Yes, I think so. I think since this is low, so reject H0. So if I had flipped my coin 10 times and 9, 10, 1 or 0 of them came out to be a head, then I would reject the assumption that the coin was unbiased. So the calculation I've done here is very precise, but what's my standard? Where is the cutoff between low enough, a p-value low enough to reject the null hypothesis, and a p-value that's too large to safely reject the null hypothesis? Well, traditionally, if the p-value is low enough, of an experimental result is low enough, we reject the null hypothesis. If the p-value of an experiment is not low enough, we fail to reject the null hypothesis. If we fail to reject the null hypothesis, that doesn't mean that the null hypothesis is true necessarily. It only means that we don't have enough evidence to say one way or the other. And in that case, we retain the null hypothesis. We fail to reject. In that sense, the scientific process is small c conservative. You need a lot of evidence to change your view, but then you do. But if the evidence is weaker, then you retain the current view. You conserve your current understanding of how things are working because not enough evidence has come along to move you off of that. And that's probably a good idea because we don't want to be flipping back and forth between explanations all the time. So how low is low enough, finally? Traditionally, the standard is set at 0.05. So p equals 0.05 is the boundary. That's 5%. So if the experimental result you see is less than 5% likely to occur under the null hypothesis, then you reject the null hypothesis in that case. And that's what we call being statistically significant. A statistically significant result. Right. Now, there are some issues with this approach, some subtleties, some nuances that we're going to want to go into. That's going to be covered in some subsequent videos. So stay tuned for that and continue to do the reading. Hopefully this helps to ground you a little bit as you're going through and reading about some of the issues surrounding the hypothesis testing and p-values. And